Hi guys, in this video I will be talking about electric potential. So far we talked about electric force, electric field, and today we're going to move to the last part, which is electric potential. So what is electric potential? So assume you have a charge, alright, and if you have a charge, then this is going to have some potential around itself. So what does that mean? It's going to have some potential energy, and it is going to be able to do some work. Alright, because let's say you have potential energy in regular cases. If you drop an object that has a potential energy, it's just going to start moving, right? So just like this, if you place something at any point that this charge creates a potential, then you're going to observe a movement. So, and the magnitude depends on the charge amount. So, for example, here we are seeing that it is 8.37, but here we are seeing that it is 6.5. So, well, this is negative charge, this is positive charge, and then they are just one charges. So we are not able to see that clear in this picture, but this one we can say that it's closer to the charge, and sorry, this one, the first one is farther away from the charge than the second one, because potential will depend on the distance, but as you get farther and farther away from the charge, you are going to have less and less charge, less potential. And of course, the amount of charge that you have over here will also determine your potential. As you have greater charge, then you're going to have a greater potential. And it is measured in volts. And a symbol for potential is also given by V. So the unit and the symbol of the variable is the same. It's capital V. So you shouldn't be getting confused with those two. It is a scalar quantity, so there's no direction. There's positive and negative potentials, but that positive negative potential is because of the sign of the charge. So if you have a positive charge, then it's going to create a positive potential. If you have a negative charge, then it's going to create a negative potential. And it is going to be given with the following equation. Potential at a point is basically K, which is electrostatic constant, which is 9 times 10 to the power of 9 times charge divided by distance. Alright, let's start with a question. So let's say we have an object that has 3 times 10 to the power negative 6 coulombs of charge, and then we have a point P that is 0.3 meters away. What will be the potential at this point? So we basically use the sub representing that we are looking at the potential at point P, and we basically use straightforward the equation. It's kq over distance, and we just plug in the numbers. K is given as 9 times 10 to the power of 9. Charge of the object that we have is 3 times 10 to the power, 10 to the power of negative 6. And you got to be careful with the sign of it because it's a scalar quantity, but the sign of the charge will determine if it's going to be a positive or negative potential. It doesn't determine the direction. And distance, which is 0.3 meters. And once you put all of them together, it's going to give you 90,000 volts. Alright, so if you have more than one charge at a system, then what's going to happen? So in this case, you are going to basically find individual potentials. Let's say you're trying to figure out the potential at this point, and you have Q1, Q2, and Q3. So what you need to do is you just basically use the potential of every single one of them individually, and then of course include the individual distances and individual charges, and you just add them together. But you need to be careful with the sign of the potential because, like we said, it's a scalar quantity, but sign will determine if it's a positive potential or negative potential. So you just find them individually and add them together. So if you want to see an example, we are trying to figure out the potential at this point. So what are we going to do? We're going to figure out the potential this guy creates at point P, the second charge, and the third charge. So we're going to find every one of them, and then at the end we're going to add them all. So a way for us to calculate potential 1, potential 2, and potential 3 is basically KQ over D, but you basically use the individual charges and distances. And how do we find a potential at the end? We basically just add V1, V2, and V3. So what is V1? It is KQ divided by distance. So K is known, Q is known, and distance is known. We just basically plug them in and find the answer. So once we plug them in, we find the potential at the first point, or potential at point P created by charge 1 is 90,000 volts. And if you go to the next one, so here we have a negative charge, so you have to include that negative charge. So it's a similar thing, and you just use the charge of the second charge and the distance of the second charge, because it's 0.3 meters away from the point that we are looking at. And once you put all of the numbers together, then you find that it's negative 300,000 volts of potential. That's what we create over there. And if you look at the third charge, and again you use the K, its charge and the distance that it has, and multiply all of the numbers and divide it by 0.2, then you calculate it as 675,000 volts. Then we found all of the potentials. All we have to do is just adding them all, and once you add them all together, then you find that your total potential is 465,000 volts, or you can also write it down as 4.65 times 10 to the power of 5 volts. Alright, so you individually find the potentials and add them together. You just need to be careful with the sign. Alright, so let's see another example, which is a little bit easier. If the potential created by charge Q only, so this guy only creates a potential V at point P. So VQ is actually equal to V. Then what is the total potential at point P? So in this case, VQ, how do we basically calculate that distance? Since this is basically a square and then it's basically at the center, then all of the charges are d distance away from that point. So my distance is going to be the same. And my K is also a constant, so the only thing that determines my potential is the amount of charge that I have and the sign of the charge. So charge of the Q is basically V, that's given. So KQ over D is given as V. Then what are we going to do? To be able to find the total charge, we basically need to find the potential created by this 2Q, negative 2Q, and then this 2Q. Then we basically K 2Q divided by same D, and it's basically just 2 times of the first one that we created. And if we look at the second charge, or actually the third charge over here, it's also 2Q times K divided by D, which is 2V. And if you look at the charge or the potential that the negative 2Q creates, then what are we going to have? K stays the same, but negative 2Q divided by D. And this guy is going to create negative 2V. And once you add them all, you basically have 3V potential at the end. Alright, so electric potential difference. So it's like the name, potential difference. So whatever the potential at a point and another point, you look at them, get the difference. That's potential difference. We're going to have 2 different ways of measuring it. So this version is a little bit easier version. So you're going to basically, let's say we are trying to figure out the potential difference in between A and B. So then what does that mean? And actually there's an important part over here. It says potential difference from point A to B. So A and B, so the second one that we use is basically considered as final, and the first one that we use is considered as initial. So the difference is always found as final minus initial. All right, so that's why the order of points is important. The first one that comes is the initial. The second one that we have is the final potential that we're talking about. And if you want to find the potential difference in between the points A and B, then we need to subtract the potential at point A than the potential at point B. Alright, so that's an important detail. And after that, we just basically look at the potentials at those 2 points and then get the difference. So potential at point B is 6.59, and the potential at A is negative 8.38. And this negative comes from the equation, final minus initial. Then this negative sign is because of the charge. Then you basically find the potential difference as follows. But there is also another definition of potential difference, and it's related with basically work. So we define potential difference delta V as work per unit charge required to move a charge between the 2 points that is in an electric field. So let's say those lines are basically the electric field lines. So that means electric field is basically created with charge. So that means we have some charges around that we don't know, but we have some electric field. So within an electric field, to be able to take an object, to be able to take a charge from one point to another, you have to do work, because it's going to require different amount of force to keep it at different points. Then it's going to require a force for you, and this force is going to require work. So that work per charge that you are applying is going to tell you the potential difference in between those 2 points. Alright, so if you put a positive charge Q at a point A, the field will exert a force F on the charge in the direction of the field. And if you want to move the charge from A to B, we must do the work. And if the work is divided by the charge Q, which charge are we talking about? The charge that we are moving from one point to another, it gives the potential difference in between points A and B. And another important note, the potential at the infinity or too far away is going to be considered as 0, because remember, we are going to have potential as kq over distance. So as you go farther and farther away, you're going to have less and less potential. So that's why as you go farther and farther away, which is the infinite or infinity, then you're going to have 0 potential at infinity. Alright, so let's see another example. So this is basically the continuing from the first questions that we solved. We had object 1, and then we found the potential that it creates at point P. And now what we are trying to do, we are trying to bring another object from infinity to the point, and then they're asking what is the work that you need to do to take it from infinity to that point. So then what are we going to do? At first example, we found the potential at point P as 90,000 volts. So object 2 is brought from infinity where the potential is 0. So what are we doing? We are basically bringing an object from 0 potential point to a 90,000 potential point. So what does that mean? We actually have a potential difference. So we have a potential difference, and we have a charge that we are moving within that potential differences. So then what are we going to do? We are basically going to go with the equation. Second equation that we use to find the potential difference. So my potential difference is going to be from P to infinity. And it's going to be equal to the work done on the charge that we are moving. And then potential at P is my final location minus potential infinity, which is the initial location. So final potential minus initial potential. and it's going to be equal to basically work divided by the charge amount that we have. And once we plug in all of the numbers, at P we had 90,000 potential, at infinite we have 0 potential, and it's basically work divided by the charge that we are moving around. So you see this guy, the 3 times 10 to the power negative 6 coulombs of charge, creates the potential, but 1 times 10 to the power negative 6 charge is moved within the potential differences. So this is basically the key. So if you are confused, like which one do we use as this Q, because we have 2Q, so this Q is the one that you are moving in between the potential differences. And once you basically put all the numbers together, then you find the work that you need to do on the charge as 0.09 joules. Alright, equipotential lines. What is this equipotential line? It is contour lines on a map. So what do? They basically represent the altitudes, right? So the one that you have as the other is going to basically have 0, because that represents the ground, and then depending on the scale, each layer is going to tell you a certain increase, and the line that we are representing is going to tell you the same altitude, because if you look at the map, this is basically the outline of the mountain. So this outline is also going to tell us the view of the mountain from the top. So that means the first layer, the first loop, let's say, is going to have the same altitude. Alright, so that is about the heights, but equipotential lines are going to be about potential. So we're going to use similar method, but we are not going to just use altitude, but we're going to be talking about potential. And about those equipotential lines, there are certain rules, because they are not just sketched from for no reason. They have some rules, and we need to know what those rules are. So it represents the line which has the same potential all along. Alright, and another important point, equipotential lines are always perpendicular to the electric field lines. So remember, when we had a charge, we were basically having those electric field lines. So those two are different lines. These are your electric field lines, but your equipotential is going to be a line that is perpendicular to this line. So that's why if you look at the perpendicular lines, then how's it going to look like? If you actually combine them all, you will see that it's going to look like circle. Alright, so they are perpendicular to the electric field lines, and electric field lines point from high potential to low potential. Remember, electric field lines, they have direction. So that direction, if equipotential lines are given, then you're going to go from high potential to low potential to represent your electric field lines. And electric field increases as equipotential lines gets closer. So what does that mean? So, for example, if you look at this part of the map and this part of the map, so what is the main difference in between them? So here you are on the ground, and then here you are at 30 meters or whatever the scale is, let's say 30 meters height. And you are basically going that short distance to be able to go 30 meters up. So it's going to be a really steep angle. But here in this part, what is happening? You are basically changing the same amount, but you are not changing it directly. So it is basically going to be less steeper. So just like this, having two lines pretty close to one another, that means the potential electric fields in that region is getting higher and higher because you're getting closer and closer to a higher potential. So as those lines get closer to one another, the fields is going to be getting stronger at that region. And the last one, movement along an equipotential surface requires no work, because remember we defined work as change in potential. So coming from this location to this location, it doesn't matter how far you travel actually, your altitude is not going to basically change. So that means you are not going to require to do work against gravity, which is acted on the vertical axis. So just like that, if you are moving along the same equipotential line, then that means you don't need to do any work because there's no potential difference. Alright, so what do they look like? So if we just have a point charge, just a circle, and equipotential lines are circles, and a sphere centered on the charge is an equipotential surface. So this is my charge, and those red lines are my equipotential lines, and those black lines are my electric field lines. Alright? And equipotential lines are in loops. Alright? If there's no zero potential, any line, like any potential besides zero, is going to have basically a circular pattern all the time. I mean, not circular, a loop pattern. So you have to connect it. And as you can see, there is no direction for electric field equipotential lines, but there is a direction for electric field lines. So these are the main differences. And what else did we say? We also said equipotential lines and electric field lines are perpendicular to one another. So if you look at the individual points, the electric field lines are equipotential lines, which is the red line, they are always perpendicular to each other. And once you put all of those perpendicular lines together, then you basically have that circular shape. Alright, and we also have different, like, couple of circles that is going closer and closer. And as those circles get closer and closer to the charge, the distance in between two red lines is also getting less and less. So what does that mean? So I would like to go from here first. If the equipotential lines are separated by the same distance, then you do not see the same amount of change in the potential. So for example, as you go from first point to the second point, it is decreasing by 8.7. But once you go from second line to the third line, which is the same distance away, but the change over here is just 3 volts. And once you go from third distance to fourth distance, then the difference is basically 2.5 volts. So as you can see, the first change is drastic. So it's basically going from 1 unit to 2 units of distance, but the change is basically 8.7. And the next one, it's 3, and the next one is 2.5, and probably the next one is going to be 2.2 or something. So the decrease will be less and less. So that's if you go with the same distance. But if you wanted to see, let's say, 1 volt, 2 volts, 3 volts. So if you wanted to have the same difference in between your equipotential lines, which mostly the same, like the case, because here, remember, each line represents the same amount of change. So equipotential lines basically tending to do that follow that rule as well. So each potential line is going to have the same difference in between them. So if this is 1 volt, then this is 2 volts, and this is 3 volts. But since they are not changing linearly, then it is going to have an decreasing amount of change in between the lines. All right, so if you just go with the same distance, the change in between the potential is not going to be the same. If you want to have the same change in between two lines, then you need to get closer and closer to one another. All right, so it is from a point charge, but if you also have like plates, so actually I didn't talk about that in the previous lecture, but this is also another part. So instead of having point charges, if you have plates, then that means you're going to have like infinite number of charges close together. So they're basically a straight line. And if you have two straight lines, charges put together, then the electric fields in between them is going to be a straight line. So here, electric field lines are not straight lines. I mean, the lines are straight, but they are not basically going parallel. They are going radially outward. But if you have two parallel plates, then the electric field in between them is basically straight line. And what was the rule for equipotential lines? The equipotential lines are perpendicular to the electric fields. And if you continue to create the same perpendicular, then you are going to basically have straight equipotential lines in this case. All right, and the green lines are your equipotential lines, and the pink lines are your electric fields. All right, and as you can see, they are perpendicular to each other. And if you have a circular one, same distance away is not going to create the same amount of potential difference. But for parallel plates, the case is a little bit different. So since you are basically having a uniform electric field in between, then the separation or the same amount of separation is going to create same amount of potential difference. So as you can see, this is the 0 point and it's 1.5 volts. And every 0.6 millimeters that you move, your potential is changing by 1.2 volts. So 1.2, and it's actually decreasing. So it was 1.5, 1.2. So what is a decrease? It is 0.3. So then in the next line, you will also decrease by 0.3, which is 0.9, 0.6, 0.3, and you have 0 volts. All right, so you basically look at the beginning and end potentials. The potential difference is 15, and you have basically 1, 2, 3, 4, and 5 basically changes. Then you basically divide it by how many changes you will have. So you're going to have 5. Then you basically find the amount of change in every step. All right. So that's how we actually draw the equipotential lines for two parallel plates. All right. So let's look at the questions about those. So you basically have a system. It says outermost is 50 volts and the change in between each line is 10 volts. So what do we expect? The outer layer is going to basically have 50 volts. And what do we know? As we get closer and closer to the charge, we're going to basically have more and more charge. So what does that mean? This is going to be the 60 volt line. This is going to be the 70 volts. And after this, we're going to basically go for each circle individually, but they're going to have the same potential, 80, 80, and then we probably need that one too. So 90. This guy right there is also 90, and this is 100, and the inner layer is going to be 100 volts. Alright, so that basically tells us the potentials at those points. And what is the question? The absolute value of the electric potentials 50 volts indicate the values of the potentials included in the sign at the labeled points. Alright, so we basically look at it. So at point A we have 60 volts. At point B it is basically not the 70, but it is the 80 line. So it is 80 volts. At C we have basically 100 volts. Alright, all you have to do is basically figure out, or whatever they give you, you basically take this as a reference and then look at the differences in between each line, and then you just increase or decrease with that same amount. And also recognize that as you get closer and closer, you're going to have a greater and greater potential. Alright, so this one is not that uniform, or it's a little bit different shape, but let's see what's happening. So draw arrows at point L, N, and U on the diagram to indicate the direction of electric fields. So they are asking for electric fields. So what did they give us? So you see these are the potential lines. So these are equal potential lines. As you see, this is changing by 10 as well. But the shape is different because you probably have random charges put on the field, so you don't really have a uniform potential. So potential lines are given, and we are trying to figure out the electric field. So what was the relationship in between the field lines and the potential lines? They were basically perpendicular to one another. And that is rule number 1, but we are trying to figure out also a direction. And what was the rule for direction? Direction of electric field lines are going to go from high to low. So what do we see? We basically go from 50, 40, 30, 20. So left side is basically going from high, and this is negative 40. This is the low side. So your electric field lines are going to be tending to go in the right direction, because left has the high potentials and the right has the low potentials. And field lines are going to go from high potential to low potential. So we figured out the direction, sort of. Now we need to figure out the lines at the given point. So my first point is right here. So what did we say? We are going to have electric field lines perpendicular to the potential equipotential lines. So my line is going to be something like this, perpendicular, and the direction. Since this is a higher potential, this is a lower potential, then the direction of that point is going to be like this. And the next one is N. So we are going to basically have a perpendicular line, and it's going to go from high potential to low potential. So its direction is going to look like this. And the last one is U. So this is going to look like this. And again, it's going to go from high to low, 0, negative 10. So 0 is greater than negative 10, so it's going to go from 0 to negative 10 direction. So these are the electric field lines at those given points. And the other question is, at which of the letter points is the electric field E greatest in magnitude? So the other note that I had was, as the potential lines get closer and closer to one another, then the change is getting greatest, and that requires basically a greater electric field. So you basically try to figure out the lines where they are closest to each other, and in that case, T is going to be the point where you have electric field is the greatest. All right, next one is about parallel plates. So they basically give you potentials at R, S, T, and U. And they also define VRS as the potential difference in between R and S, ST as the difference in between those two letters, and so on. And they are basically asking for how do the magnitudes of these potential differences compare. And if you remember, we said as you go from one plate to another, then your potential is going to change. And that change is going to happen as you go like farther and farther, and the separation in between is the same. So let's say this is 0, this is 1, 2, 3, 4, 5, and 6. So that means as I go in the horizontal distance, then I'm going to have more and more potential difference. So I'm basically looking for the most difference. So VSU is going to have the greatest potential difference. And which one is the next most separation? So TU and ST, they are, when you look at them, VST is going to have a little bit a greater gap, so that means the potential difference in between ST is going to be greater than VTU. And what is the potential difference in between R and S? Remember, we said along the same potential line, we basically have no potential difference. So this is the potential equipotential line for me. So that means along this line, I have no potential difference. So VRS is actually equal to 0, and so that it's the lowest. So my answer will be A in that case. All right, the last question. So this time you basically have 2 volts and 10 volts, and they tell you the separation in between them is 0.04 meters, and then they're asking for what is the potential at point P, which is 0.01 meters away. So in this case, we basically try to figure out the pattern. So it's going from 2 volts to 10 volts, so that means the change is 8 volts. And how do we, or what is the distance for us to make that change? It's 0.04 meters. So then what does that mean? Every 0.01 meters, we basically change the potential by 2 volts, because when we make the change by 0.04, I need to have 8 volts of change. So that means for every 0.01 meter of distance, I need to change the potential by 2 volts. And what are they asking me? They are asking me that distance away, so 0.01 meters away. And what did we decide? Every that much of a distance, we need to change the potential by 2 volts. And my starting potential is already 2 volts. Then what should I have? I need to have 2 volts plus 2 volts, which is 4 volts at point P, so that every time that it actually increases by 2, once it reaches to 0.04 meters, it should be able to get 10 volts. And why did I increase it but not decrease it? Because it's basically going from 2 to 10, so it's increasing. So we need to add that potential difference. All right, so that is your electric potential lecture video. Thank you for watching.